This presentation is about a library I've been working on for a couple of years. It's more like a library is kind of an experiment, and more like a presentation is like a plea for help. The story of this, I started like in 2013. I went back to school because they have a very cool functional programming department. I took this category theory course that has half category theory and then generic programming. It was mind-blowing and was really interesting. And part of the course was a generic programming, kind of a library. Was a small Haskell program that does generic programming using the techniques that we saw in the course. And I was kind of bored. And a year later, I was kind of bored. And I decided to translate this to Scala. And then I started like running against all weird corner cases, find out that I know barely about the Scala compiler. But I somehow managed to get it work. But it has a couple of ugly casts because type information got lost in the middle. One day I showed that to Miles Hyben and said, Miles told me, we should be able to get rid of those casts. I couldn't, and that was my goal for the last 2 years, but something like every a couple of months I go back to this, think about it, try something doesn't work, I put it again in the freezer. But anyway, it's still I like the ideas, and I wanted to present a little. For what I could understand, is almost the same as Matryoshka, just with different names also, almost. The whole thing is based. There's a couple of things. First, this is kind of the categorical definition of fault that, based on one initial algebra, you have the fault is the isomorphism between that and all the other algebras. That means basically we are the initial algebra, the constructors. With fault, we are replacing constructors with different functions. But one thing we can do also is we can create an algebra that describes the data types. If I recall correctly, there's an evolution. You can take every constructor you have and extract something called sigma algebras. That basically is an algebra that counts how many parameters you have in every constructor. And then from those constructors, from that sigma algebra, you transform that into a functor algebra. Basically, you add a parameter, and then now you have functors, and then you can apply fault. The decomposition for the regular cases is like this. All these are actually functors, but you need a unit for the empty values, constant to hold values. I have an identity functor for the recursive type. The left injection, when you have alternatives, this is represent the left side. The right injection of the sum, when you have alternatives that represent the right side. And when you want to put two things together, you have the product. That's the interesting thing is seeing an example. We have I think I have the list definition here. We can have well, it should be easier, but let's say we have the definition of list of a Haskellish. We have nil or list of the cons of a list of A, kind of, right? What we want is we want to describe this with these functors. So first we have the thing that doesn't have any value. That's the U. That's the left side of something. So this is actually a sum. And on the right side we have a combination of one element with a recursive type. So it's one element. We need the constant to keep the element, and combine it with a recursive call of the type. And we can do the same with a tree of A. Let's say you have the leaf of A, or a tree or a, what do I call it? Branch of tree of A and tree of A. And the way we describe this is, okay, in one side we have the constant holding the value, and otherwise we have a recursive type combined with another recursive type. The thing is, with this algebra, we can describe a lot of it's like regular types. And what we're going to do now is we can define a fold for this algebra. So if we have a way to go from any of those regular types to this algebra, and then we have a fold for this algebra, we can have only one fold that folds all these kind of data structures. And that's what this Haskell code does. It doesn't use first it creates data types for the algebra, and then it has the interesting that for me was complicated. It uses type families to go from the regular type to this decomposition, and from the decomposition to the regular type. And then it defines a so here is the generic fold. This is actually I checked it once, and this is the same code as the we call it the mu, or
this is for fix.
Yeah, fix. It's the same code as fix, because I was trying to compare, because Matroska seems way better. I was trying to extract some tips and tricks, and I checked that it seems way. Anyway, so I sat one day, I started writing the Scala code for that. My first problem was Scala doesn't have type families, but by the way we are using here, I actually can combine I can use a type class that actually has a type, and that will be the use of the type family in the code. But I didn't want to depend, because this was an experiment, I didn't want to depend in any external library, so everything is bespoke, hand-coded, custom-made, and locally sourced. I created my own functor class. I started to create the case classes for the elements I want, constant, and the functor class for constant, the unit, the functor class for unit, the identity, the sum with left and right, the functor for the sum, and the product, and the functor for the sum. This one I'm actually not using it, but this is the composition of two different functors. I'm not using it for the code I have, but so far this part worked out relatively good. This is kind of the core of the whole thing, where I define my regular class data type that takes your type and creates the generic version of that. I need the actual description of the type, the functor for that, and the functions that go from back and forth on that. With that, I can write my generic fold that takes, and this is where I got really crazy because I was trying to emulate because I was following the Haskell code. I might end with painting myself into a corner. But right now I have the regular for the data type, and then I need the actual, this is called the pattern functor. That is the description in our small components. But I need to project also, I need to pass the value that will be the output of the fold. For that, I just need to ask. That is, I need to have the regular for that. And this is the function I'm going to fold from the pattern description of that of a type generic into an A, and that's what this code does. And this kind of works, surprisingly, for me at least. So then I went to data types. I create a couple of sample things. I create a tree that is not parameterized, that is fixed on int, doesn't have any parameter. So I create the regular type class for that tree with a description of the functor. Ideally, it should be like this. The type of the tree is the type of the leaf plus like a sum identity, product identity. Oh yes, sorry. Yeah, I forgot that. Yeah, that's good enough. But it turns out this works. Scala recognized it. I was worried I didn't recognize it. But if I write it like this, it doesn't find the implicit functor for that. I showed this to Daniel Spear and he told me, oh yeah, this is a bug in the implicit resolution that it doesn't work. It turns out if you do it like this, it works. If you go step by step, it works. Anyway, what's good for me? Then I have to write how to go from this tree of integers to this pattern functor. So if I have a leaf, I have the left of a constant of that value. If I have a node branch, I have the right side of the product of both two identities. So the other side is just the same thing in the opposite way, right? From left constant, go to the leaf, and from right product, go to the node. One thing it actually work is also I can use the regular Scala list. I don't have to create my own type. I just can plug the Scala list. Again, a list is the unit or the product of a constant and the regular type. And we do the same trick. We decompose that into the components to the implicit works. Nil is the left side of unit. Right is the XXX, like head, tails is the right side of the product of the head with the tail, back and forth. I define here my binary tree, just to try different things, right? We have the leaf and the node. This is almost the same as the tree before, but this is parameterized. Again, it works. I mean, I can write this. I will not say it works, but I can write this. It compiles. This is something I was still working on. I can use bifunctors to work on types that has different types inside. Like the example is a rows tree that is a tree of list and a tree of list of trees. Here with the simple regular functors, we cannot represent that. But with functors, yes, because in one side you hold the parameter, and on the other side you hold the different type, and then you go recursively. But I was started working on that. I got blocked. I said, okay, let me try to first make the simplest case work. So yeah, I'm not going to show that. But then we have kind of all the elements in place. So right now, to make it work, I have an example. I've had this integer tree with just to leave 1 and 2. I have the other tree that has parameters. This again parameterized to integer. I define here like no, leave, whatever, and just a plain old Scala list. And I'm going to define, in this case, I want to define a sum of all the elements of the data type using my components. So the sum of the empty thing is 0. The sum of the constant is the content of the constant. The sum of the identity is just the identity itself. It's basically a marker to just keep recursing. The sum of the left side is, again, the sum of what is inside. The sum of the right side, the same. And the combination is, in this case, is just a sum of the result of summing both sides. That's kind of the thing I'm not happy with. This is get really ugly, and you have to put the types, otherwise somewhere this is inferring any. Maybe I'm asking too much from the Scala compiler. I don't know, I'm just trying to make it a little neater. I can do the same. This is my sum function, and here I use fold with sum. I use just a different data type, but the same fold function and the same sum function. I can try the same for count. Basically, the count of empty is 0, the count of k is 1, and all the other things are kind of the same. I can use it for max. That's almost like the sum, except that when I go a combination, I just select the max one. I was trying also flatten. That takes any data type and writes it into a list, because again, for the empty case is nil, is the empty list. When I have one element, is the list with an element, and when I combine two elements, two types, I just concatenate the list. There's something I was trying. This writes everything into a string. This checks. I can use to check Boolean properties. But let me run it. I mean, basically, you see the code is the same shape always, and I can run the same thing for these different data types. So if I run it, I get a lot of warnings saying, okay, you're explicitly saying the types here. You're lying to me. Let me put that bigger. But in spite of the complaints and the lying and whatever, it works. I can calculate the sum of the tree parameterized in int of a list. I can count the elements. I can get the max. I can flatten into a list. I can serialize into a string. I can get I can check a property for each element. I can check a property that combines all the elements, because I define it like for all and exist. I can check, this is the all and this is the exist. So, So, besides that, this is probably everything here is like duct tape and glue and whatever. It's kind of horrible to look, but I think the idea itself is really amazing. I think it's what the Matryoshka does, is with only one function to fold your types. You can use any other type and have only one function. It will work. You don't have, if you change your other type, you don't have to change your fold function. That's what I wanted to show. And if somebody has ideas, I'm totally open to that. Thank you. Well, if anyone questions or whatever.
So it seems derive this regular thing, right? Like we want to like have that automatically be derivable, right? And you can just do all these things for any tree shape.
Yeah, one of the ideas I had once I make this pretty is like this step is pretty mechanic. I mean, you can write it when your hand closed. I was going to look at if we can write a macro that generate this, because it's pretty mechanic. You can describe it based on the constructors. You can analyze the constructors, generate your regular components, and also write the functions. Well, probably that will be, even before like fixing those catch, will be interesting to do that.
Yeah, I think that would be
Yeah.
Pause at the top.
Pause.
And then save recording.
Yeah.
If you click on cancel, everything will be gone.
Smart guy. Cool. Well, thank you.